Okay, just checking that transcription is running. So good morning, everyone. I'm sharing my screen now. So we're going to pick up with our lecture. Last time we're looking at lecture 6, kind of dealing with standard error we left off on. So we're going to continue on with that for part 2 of lecture 6. So we're starting to get into more of the inferential statistics now. So today, right, we're going to be looking at more of the standard error of the mean, an important stat that we can calculate to try to see how certain we can be in that our sample estimate is representative of our population parameter. Then we'll get into a little bit of sampling error and sampling methods for this video today. Okay, so we know a little bit about the standard of the mean, and what we use it for is that we're trying to estimate some population parameter. Of course, we cannot go out there and measure everything, so we have to take a sample to try to estimate whatever that population value is. So we have to have some way to estimate how good our sample stat is at representing the overall population stat, right? Usually in this case, we're talking about something like the mean. Right? We're trying to use a sample mean to represent what the population mean is. But we can do it for anything, right? We can do it for range, we can do it for standard deviation, but for the most part, we're trying to look at using a sample to estimate central tendency, right? Mean, median, mode, things like that. But usually we're talking about the mean, a little bit about the median. So what we use a standard error of the mean for is that we can calculate what's known as an error range, the sample mean. That tells us a little bit about the chance of the population value falling within that range. Remember, range is a high value to a low value, right? So essentially the standard error of the mean is giving us a range at which we can have a certain likelihood or probability that the population mean is going to fall within that range. So this is essentially what the standard error of the sample mean is, right? It's calculating the error, how much error we can expect from using our sample mean to predict what the population mean is going to be. And essentially, it comes down to, we saw this last time, the standard error of the mean, SE, standard error, is calculated using this formula, where S is the standard deviation of the sample, and then N, we all know now, is the population, or the sample size, I should say. How many values are in your data set? And that is the square, taking the square root of the number of observations in the sample. So I showed you there that standard error was using the sample mean, S, or sample standard deviation, sorry, to calculate the standard error. In a perfect world, we would have the population standard deviation to calculate the standard error. But often we do not know, just like with the population mean, we do not know what the population standard deviation is. But if we did know the population standard deviation, it'd be a very straightforward calculation to determine the standard error, right? We would just take, in this case, our example here, we have a standard deviation in a population of 17, sample size of 5. So very straightforward calculation of the standard error. 17 over the square root of 5 is going to give us a standard error of 7.6. But often, and most times, we do not know what the population standard deviation is. So how can we figure or approximate what that is? Well, again, we're going to use the sample. And so we're going to approximate the population standard deviation, right, using the standard deviation of the sample. So remember that there's a subtle difference between the standard deviation and how they're calculated from a population, right, where the standard deviation, right, is the square root of the sum of all the differences between each value in the mean divided by the sample size n. S, right, the sample standard deviation, similar formula, but because it's smaller, the sample is smaller than the population, we correct for this difference by dividing, instead of n, dividing by n minus 1. So essentially the formulas are the same, the slight difference, right? So essentially what we're trying to do is that we're taking our sample, we're trying to approximate the population using that sample. So usually what we're trying to do is use our X bar, our sample mean, to estimate what the population mean mu is going to be. And in order to calculate the standard error of that estimation, we're going to use, because we do not have the population standard deviation, we're going to substitute it instead using the sample standard deviation S. So the standard error, you might be wondering about the term standard, why is it called standard error? Well, it's very similar to the standard deviation, right? Remember we looked at Z values and how standard deviations can be normally distributed around a mean, right? So basically standard deviation, right, is a measure of the observations and how far they're dispersed away from our central tendency, our X bar, our sample mean. Our standard error is a measure of how the sample mean relates or does not relate to how much error we have to the population mean. Also has the word standard in it because we'll see that the error itself is normally distributed. So usually that's the assumption that we're making. Remember the central limit theorem, right? This is it. So what am I talking about here? Well, again, let's assume that we have this nice normal symmetrical standard or normal distribution with our population mean in the middle, positive standard deviations going to the right, negative standard deviations going to the left. Essentially what we're trying to do with the sample mean is like, you can think of it as a bullseye. We're trying to estimate what that population mean mu is. We do not know what it is, so we have to estimate it using sample means. Right? So our X bars, right? There's one sample mean. There might be another sample mean there, another one there. They're all not exactly going to give us a match for the population mean. But over time, what we should see that those sample means, those X bars, should, if we take enough samples, should form a normal distribution. And we can use that normal distribution and the assumptions with it to try to estimate how much error is associated with using a sample mean to estimate the population mean. Right? So again, the idea is that with our normal distribution, we know that most of our values are going to be clustered around the midpoint. So the more samples or X bars we take, the more certain we can be that we're better approximating the overall population mean. So you can also think about the standard error of the mean in this way. Imagine that you're trying to estimate some variable, right, across a number of city blocks, say in New York, right? So you're going to different neighborhoods and you're measuring whether it be income or whatever parameter that you're trying to quantify. So you're going around to these different neighborhoods, and those neighborhoods are giving you a sample mean, and you're trying to use that sample mean to estimate what the population mean is going to be across all of Manhattan, or maybe all across the total city of New York. So the sample error of the mean also gives us how much variation we should expect between our different sample mean values. So imagine we go, right, we take these different samples here, right, all these X's are indicating different observations. So this is our sample 1 here, sample 2 here, and we can take as many samples as we can, right, sample N right there. We take the mean of each of these samples, and we can see the standard error of the mean gives us an idea of how much variation or difference we should expect between the means of each of these different samples. So again, that's why sometimes it's called the standard error of the mean, sometimes it's just called the standard error, but they're the same thing. So what causes the standard error to become greater or lower? Well, just based on the formula itself, it's only based on two variables, right? The sample standard deviation and the sample size. So as we increase the standard deviation of the sample, in other words, as S gets larger, we're going to expect there to be a greater standard error. the uncertainty is going to be greater. And why is that? Well, if there's more variation in our sample itself, right, through our sample, that indicates that the population also likely has a larger variation. So there's more uncertainty in using our sample mean to estimate our population mean. So as our sample standard deviation gets larger, our standard error, or our uncertainty, also increases, right? So as S goes up, so too does the standard error. On the other hand, as our N, sample size, increases, as we take more observations, right, take more samples, just because we have, remember I was showing you with the normal distribution, our standard error will go down, right? It's in the denominator, so anytime the denominator is going to get larger, that's going to decrease the standard error. So as our sample size increases, we can expect that our standard error is going to decrease. So here's two sample means, X bars, both with a value of 100. But you can see that there's different errors or uncertainties associated with these two distributions, both of these X bars. They're both 100, but you can see the standard error for the mean for the blue sample is much less than the standard error of the mean for the red sample, right? Although they're both giving us the same estimate, there's different levels of uncertainty associated with both of these samples. And that uncertainty comes down, right, a lot of times to the sample size. So here now we have three different standard error of the means, right? All three of them with different sample sizes, with the blue having the largest sample size, 48, the purple, the middle, 17, and then the red being the smallest sample size with 5. So because our blue distribution, right, has the largest sample size, its largest N, its standard error is much lower than the smaller sample size in the red. All three of these are giving us the same estimate, right? But because the smaller N, right, has a smaller sample size, it gives us a larger standard error of the mean. So there's more uncertainty with the smaller sample size. So often we can also illustrate how much uncertainty we have in an estimate using the standard error. In graphical form, we can use the whiskers or the error bars to represent the amount of uncertainty. So here we have some parameter, maybe it's height, right, between men and women, right? So these column graphs will be indicating the mean height for men there, mean height for women, and then these whiskers, these error bars, are representing the standard error of the mean. Basically the amount of uncertainty we can expect in how well that sample will represent the overall mean. Okay, so let's do some examples because that best illustrates how we can use the standard error to estimate uncertainty between samples and populations. So imagine we go out there and do a sample of 10,000 people across BC. So that's our sample size, N equals 10,000. And what we're interested in is finding out how many pints the population of BC, the average person, drinks during a week. So we go out, of course, there's millions of people in BC. Our sample is relatively small compared to the overall population. And we go out and we survey 10,000 people, and we get the result back that on average, we have a mean consumption of 5 pints per week. We also, from our sample, get a standard deviation of 2 pints per week. So there's our data right there. Our sample mean is 5 pints per week. Our sample standard deviation is 2 pints per week, and our sample size is 10,000. So now we can calculate the standard error of the mean to tell us how well our sample mean likely represents the overall population mean. And remember that we likely never really know what the population mean is going to be, but we can estimate how well the sample mean is at representing it. So again, we're going to use our standard error formula right there to calculate the standard error of this estimate. So if we plug in our numbers there, right? We plug in our sample mean, x bar of 2, and 10,000 for a sample size n. Take the square root of 10,000, right, is 100. So 2 divided by 100 gives us a standard error of 0.02. Okay, so you might be asking, well, what does that mean? What does 0.02 mean? What does that value actually tell us? Well, going back to the normal distribution, that tells us that there's about a 68.2% chance that the actual population mean, in other words, mu, will lie plus or minus 0.02, the standard error, above and below the sample mean x bar. Right? So in other words, there's a 68.2% chance that the population mean is going to fall between somewhere between 4.98 and 5.02 pints per week. And how do we get those numbers? Well, essentially, we take our sample mean, which is 5, and we subtract the standard error. That gives us 4.98. And we also take the sample mean and we add the standard error. That gives us 5.02. So essentially, we have a 68.2% chance that mu, the population mean, how many pints BCers actually drink per week, is going to fall between 4.98 pints and 5.02 pints. So this is how you can use this standard error of the mean. So we can look at it in graphical form, right? There's our sample mean, x bar 5 pints. And by calculating the standard error of 0.02, that tells us that there's a 68.2% chance that the actual population mean is going to fall between 4.98 and 5.02. And why, you might be wondering, why is it 68? Why are you 68% sure that it's going to fall between the 4.98 and 5.02? Well, it comes down to our assumptions again with a normal distribution. And we're assuming, just like with standard deviations, the standard error, we're assuming that they are basically normally distributed. Okay, so remember that for the area or the probability underneath the normal curve, if you go 1 standard deviation above and to 1 standard deviation below the mean, that's going to cover about 68.2% of the area or probability. If you go out to -2 standard deviations below the mean, up to 2 standard deviations above the mean, right, you're going to cover about 95.5% of the area underneath the curve. And then if you go to plus and minus 3 standard deviations above and below the mean, you're going to cover almost all of the area or all of the probability underneath the curve. So sometimes it's called the 68, 95, 99.7 rule, right? 1 standard deviation or 1 standard error, you're going to cover 68% of the area underneath the curve. 2 standard deviations, 2 standard errors, 95%. And then if you go 3 standard deviations or 3 standard errors, you're going to be covering virtually all of the probability, but not quite, 99.7%. Right, so 68.27%. Extend that out to 2 standard errors or deviations above and below, you get to 95%. Then if you go all the way plus and minus 3 standard deviations, you get over 99%. So we can take this standard error that we just calculated for our beer consumption example and extrapolate that. So what if we take our standard error and we double or triple the range of the standard error around our sample mean? Well, that of course will allow us to be more confident that the population mean is going to fall within that larger range. So let's say instead of 1 standard error, right, we're going to go to a range of plus and minus 2 standard errors above and below the sample mean. So this, instead of giving us a 68% probability that we're capturing the population mean, now because our range is going to be wider, now we're going to have a 95.4% chance that the population mean is going to lie between our two standard errors below, which is 4.96, and 2 standard errors above, which is 5.04. So now essentially what we're doing is that we're taking our x bar 5, that's 0.02 is our standard error, and now if we multiply it by 2, because now we're going to use 2 standard errors, now we get 4.96 and 5.04, a larger range And so now, instead of being 68% sure, we can be 95% sure. And we can extrapolate that even further. If we want to go 3 standard errors above and below the mean, right? We extend our range because we're going to multiply our standard error by 3, so we get a larger range. So if we look at things underneath the normal distribution curve, there's our X bar, our sample estimate of 5 pints. If we go 1 standard error above and below, that gives us our 68% sure chance that we're going to capture the population mean. And then if we extrapolate that out even further, 2 standard errors above and below, right? The range gets larger, so we can be more certain that we're getting the population mean. And if we want to go real crazy, we can go up to 3 standard errors, and we can be virtually certain that the population mean is going to fall between 4.94 and 5.06 pints per week. So this is what's known as the confidence interval, right? This allows us to determine a probability that the parameter, in this case being the population mean, is going to fall between 2 sets of values or within a certain range. This is what the confidence interval is. And again, it comes down to the premise of the normal distribution, right? Where 1 standard deviation or 1 standard error above and below covers 68%, up to 3 standard deviations above and below covers almost 100%. A commonly used confidence interval is a 95% confidence interval. So this is another example here, not our pint example, but this is an example here where under our normal distribution assumption, right, our confidence interval, or 95% confidence interval, right, we're going to have a 95% chance that the population mean is going to fall somewhere between, in this case, 2.92 and 5.62. There's only a 5% chance that it's either going to fall above that interval or below that interval. So back to our pint example, right? So we have some population mean, mu, right? We do not know what it is. It could be any of these arrows that came down there. And we're trying to estimate what that is using our sample mean of 5 pints per week. So if we apply our standard error, right? If we put 1 standard error above and below it, right? That gives us a 68.2% chance. If we go 2 standard errors out, right, we get a much larger confidence in our estimate. And then we can apply 3 standard errors, which we're virtually certain that we're capturing the population mean. So we can also use the standard error equation to estimate how big of a sample we need to achieve a certain level of confidence, right? So sometimes we want to figure out how many observations or how many people we need to interview, right? How big of a sample size do we need to achieve a certain level of confidence, whether that be 68%, 95%, or 99%. So essentially what we can do, right, we can take our standard error equation and we can flip it around, do a little bit of algebra. So essentially we get n, right, the sample size that we need to achieve a certain level, confidence level, is now going to be equal to the standard deviation of the sample divided by the standard error to the squared, right? Because we got rid of that square root in the original equation. So the idea here is that as we decrease, so if we see here we have a bunch of different sample margin of errors. So you can see down here, as our sample size decreases, right, our level of error or margin of error increases. So at the bottom here, we only have a sample size of 96. Our level of error or margin of error is 10%. As we go up and we increase n, or our sample size, we see that the range, our margin of error, gets smaller and smaller. So as our sample size gets larger, or I should say in this case, as our margin of error, as we decrease the margin of error, we're likely going to increase the sample size needed to achieve that smaller margin of error. So what am I talking about? Well, let's do an example. So let's go back to, right, if we want a sample mean to represent the population mean at a 68% confidence value, or close to 68% confidence value. In other words, plus or minus 1 standard error above the sample mean. How many people would we need to survey in order to get a 68% confidence level? Well, we can use this turnaround formula now and plug in our standard deviation of our sample, and then our standard error, which is 0.02, and that gives us an N of 10,000. So that tells us that we need to survey 10,000 people in order to achieve a 68% confidence level. What if we increase that? What if we want to be more sure? We want to be sure that the sample mean is representing the population mean at a 95% confidence level. Well, you can imagine, of course, that our sample size is going to have to increase, because as we increase our sample size, our standard error decreases. Right? So if we want to be 95% sure, right, essentially what we're going to be doing is determining the lower limit and the upper limit that basically encapsulates the range of 95% of the area underneath the normal distribution curve. Right, so again, going back to our pint example, we have a standard error of 0.02 pints per week. That's our standard error. So if we want to be more certain, if we want to go from a 68% confidence level to a 95% confidence level, we need to divide that standard error by 2, right? So we need to decrease the error, the uncertainty, by 2 to get to the 95% confidence level. So we take our standard error 0.02 divided by 2, that gives us a new standard error 0.01 pints per week, a lower error. So now we're going to plug in those values, right? Going back to the idea of the normal distribution, right? We're going to plug in those new values. Our sample standard deviation is still 2. Our new standard error, because we're dividing it by 2, is 0.01. That gives us a new required sample size of 40,000 people, which makes sense because now we've gone from a higher confidence level, right? Because then we needed 10,000 people to be 68% sure. If we want to be 95% sure, we're going to have to interview a lot more people. In this case, it's going to be 40,000 people. So let's say we wanted to be very certain that our sample mean is representing the population mean. How many people would we need to survey in order to be 99% sure? So same assumptions, right? We have our same standard error. This time we're going to divide by 3, right? Because we're going out 3 standard errors above and below the mean. So we're going to divide our original standard error by 3. We still have the same deviation in our sample. In this case, we have 90,000 people that we need to sample. So of course, as we want to be more certain in that our population mean is being represented by the sample mean, we have to increase the number of observations in our sample size. So in our pint example, right, we need to survey 10,000 people to be 68% sure that our sample mean is representing our population mean. And then, right, we have to get up to 90,000 people if we want to be virtually certain that our sample mean of 5 pints is going to, the range is going to encapsulate or include the actual population mean. Okay, talk a little bit about sampling methods, last part of this video. So we're concerned about spatial data, right? So when we're conducting research, right, again, the idea here is with inferential stats is that we never have enough time or resources to go out and measure everything. Hence, we have to rely on a sample to estimate the population parameter. So of course, we want our sample to be as representative as possible of the overall population. So representative is the key word here. So here's our target population, what we're trying to quantify. And within that target population, we're taking a sample in which we're trying to estimate how much error is between the sample estimate to the overall population estimate. So we want to avoid a couple of things, right? We want to avoid bias in our samples. We can have systematic bias. We're talking mostly about random bias right now, but we also want to avoid systematic bias, that we'll talk about later. And we want to minimize the amount of error that we should expect. Right? So how do we go ahead in thinking geographically or spatially and set up a sampling program that best represents our population by our sample? There's different schemes that we can use, right? And here's 4 of them right here. So imagine each of these squares is kind of like a XY coordinate, latitude, longitude, right? It's some area on the Earth's surface. So with a simple random scheme of sampling, right? Essentially, we just go out and pick coordinates. Maybe we have a random number generator that randomly states coordinates within the square here. And we go out and we then sample those random areas. We can do it systematically if we want to do it in a perfect grid, right? We can do it perfectly spaced out like this. Just do it along in a grid like that. Want to get a little more sophisticated, we can do what's known as a stratified sampling scheme, where we divide our study area into 4 locations, and then within each location, we randomly sample from within each of those. Maybe we want to do it spatially, or maybe we want to break it down by, say, between males and females, where we want to interview or survey the same number of males and females, but we can do that through a random sampling scheme. Or maybe sometimes we do not have enough time. Say we want to measure something and we do not have enough time to get off the road. Maybe we're just going to measure along, right, close to an area, like a road, in which it doesn't take us very long to access. And then in terms of random sampling, we have something called simple random versus clustered random, right? Simple random, I showed you already, is where basically within your target area, you just go along and pick random sampling coordinates and go and survey or measure at those coordinates. And then with clustered random, you can be a little more targeted, where you randomly choose some areas within your target area, and then within each of those areas themselves, you pick random spots to do your sampling. So clustered is sometimes called nested random sampling. Right, so one thing we should try to achieve is that with our sampling, we want our errors in the data to be random as well, okay? So we have to keep in mind that a lot of our data clusters in space, so we have to be cognizant of that in order to go and do a representative survey of whatever parameter we're trying to measure, okay? Sometimes a simple random scheme in terms of our sampling is not going to be enough to accurately represent our target population. Sometimes we have to be a little more focused and divide our area up into stratified areas and then go after those stratified areas. So what do I mean by this? Well, imagine you have a population, right? And the population has, what, 12 people in it, but your total overall population has double the amount of red people than they have compared to blue people and green people. If you want your overall sample to be representative of these different colors, right, you're not going to go out and just pick at random between all these 12 different individuals. You're going to first divide them up by the color, red, blue, and green, and then knowing that you have double the reds, you're going to focus more, double the amount of sampling within the red population compared to the blue and the green. So that's an idea, the idea of kind of stratified sampling, more of a targeted approach, a little more purposeful than pure randomness. So we'll talk about some practicalities in your research, right? Always make sure, right? Think about personal safety, report back, especially if you're doing, going on a mountain like I did, doing measurements of snow and on glaciers and travel and things like that. In terms of a lot of human related, right, surveying people, often you have to pass your surveys through an ethics committee to make sure that you're not asking inappropriate questions, things like that. Practical considerations, right? The cost, the time that it's going to take for you to be out there, the accuracy of your sampling instrument. If you're going out and using a thermometer to measure something, how accurate is that thermometer, or how accurate is your measuring device? Right, so the first thing you have to look at in your steps for selecting a sample is first define what is the target population that you're trying to quantify. Right? So, for example, imagine that we want to know whether bees in Canada are affected by pesticide use. So bees in Canada is going to be our target population. And what we're interested in is whether they are affected or not by pesticide use. So the second thing we're going to do is, because of course we cannot go out and sample all the bees in Canada, we're going to set up a sampling frame. This is going to be our sample population. So imagine that we of course we can't measure all the bees across Canada. Say that we're in Quebec. That's where we're being based in Quebec. So that's where we're going to do our sampling. So our sampling frame in this case, since we're living in Quebec, we're going to get a list of 75% of Quebec bee farms. So that is our sampling frame. And we're going to take our samples, or actual observations, from within our sampling frame. Right, so then this is the point that we probably go out and determine what our sample design is going to be. It's going to be random. Are we going to target certain bee farms or not? And if we are going to target them, why? So again, we have our list of 75% of Quebec bee farms. And from within that sampling frame, that's where we're going to get our sample from. Right, so this is the point that we'd probably be determining, right, for our 75% Quebec bee farms. What's going to be the style or the method that we're going to use to sample those bee farms? It's going to be random, it's going to be systematic, stratified, or just going to be convenience, right? Bee farms that are closer to us, maybe we can go out and measure more of them. Maybe that's going to be better, but again, then we're going to have some geographical bias to our sampling. Then we're going to get into a little bit about planning your study, ethics, approvals for going on the farms, talking to the owners, logistics, how far you have to drive there, cost, gas, time, things like that. So that's also going to determine how big your sample is going to be, right? And then you're going to go out there, begin your sampling, collect your data. You're going to bring it back and then start looking at that data and start doing your analysis, okay? So say in this case, our study design was stratified random sample, right? So we selected maybe geographically some farms, bee farms in the north of Quebec, some in the center, and then some in the south part. And then within each of those segments, geographic segments, went in and did random samplings. And we also have to make sure, because we're interested, our research question is whether bees are being affected by pesticide use or not. We have to make sure that we have a comparison. We have a list of bee farms where there is exposure to pesticides and a control group where we do not have any bees being exposed to pesticides. Right? So maybe in the end, in terms of our sample, we get 50 random exposed farms to pesticide and then 50 random unexposed farms to pesticides. So we're going to collect our data in terms of bee die-offs or mortality rates. And then we're going to do a statistical test to see if whether there's any significant difference between bee health between those 50 exposed farms and those 50 randomly unexposed farms. And this brings us down to the last concept we'll talk about today, is that how well our sampling or our study does in representing what we're trying to represent, which of course is whether bees all across Canada are affected by exposure to pesticides or not. So this is what's known as here as external validity. External validity basically tells us how representative our sample population, which is the bee farms in Quebec, is that representing the overall population of bees clear across Canada. So that's our external validity. It's kind of like how well does our study translate into what's going on across the planet, right, outside of our study itself. That's what's known as external validity. And then we have something known as internal validity, which basically is how well our sample, right, in this case was 50 exposed and 50 unexposed farms, how well does our sample represent our sampling frame, which in this case was Quebec beef farms. So of course, we want our study that is maximizing both the external validity and the internal validity, but often this is not possible, right? So basically in the end, what we're trying to do is seeing if our results from our sample, how well can they be inferred to the overall target population. Okay, so we'll leave it off there for this video, and we'll get on to more confidence intervals in our next video.